Okay, well, this was pretty overwhelming, and I'm not quite sure whether I can find the words now. But anyway, welcome everyone, and it's really a pleasure that you are all here. And yeah, I'm not going to be in time either, but as we are too late anyway, I think that's still fine. So I will take you through a journey, across times and scales. I look back at some of the projects and some of the topics I had the privilege to work on, and it will be far from complete. It's really just a small selection. Many things you have already heard today, and you have heard a lot of, there are way too many nice words and things I may have achieved or may have not. And so I thought I might maybe focus a little bit more on some of the screw-ups and mishaps and failures along the journey. I start with the failure of snow, I continue with some words on avalanche formation and forecasting, and then finish with application and transfer to practice. And no doubt this picture, these iconic pictures will also show up in this presentation here. And as we have already heard, I mean, we had that picture in a paper first submitted in November 1995. It got rejected. We laid it aside. 2 years later, we resubmitted to another journal. We again had a hard time. And one of the sentences actually the reviewers didn't like was, on low angled and level terrain, the collapse of surface hoar layers may be an important source of gravitational energy for fracture propagation. Of course, there wasn't much evidence in our paper, but we just put that into the discussion, or maybe even the conclusions. So this picture, I think, have triggered a lot of interesting research. It was also the source of some misconceptions. It also triggered it was a good example of actually really poor science communication. When a paper came out by Hiley and the kit issued a press release. And I remember well that evening at the Diavolezza hut, sitting together with some guides, and they were just laughing at those scientists who had just invented that you can trigger avalanches from the flat. So sometimes it's harder to get the press release right than actually getting the paper right. Now, failure of snow, when I really started to learn about that subject was in that year in Canada, when I walked at Rogers Pass at Mount Fidelity, which is the Canadian Weissflurjoch, and downstairs in the lab at Rogers Pass. And what we figured out there in the field, we looked at how weak layers of bird surface hoar gain strength, how they also become thinner, and then on the right-hand side you see some of the lab results. Actually, what the topic was there was the temperature effect, and you can see that the colder the snow, the stiffer it gets, and they also reproduced the well-known ductile to brittle transition for shear strength, as you can see down here, which means that if you load snow fast, it fails at a much lower strength than if you load it slowly. It might not even fail then. The temperature effect we worked on further, and you have heard that Christian Campanovo and I've used a so-called rheometer, and with that we could actually really isolate the temperature effect, not without the changes in microstructure. And we also figured out that snow is actually a rheological simple material, I think something that hasn't really been exploited yet. Work on snow failure continued. So far we had used displacement controlled setups. Ingrid Reiweger managed to have weak layers within the samples. I think these were some of the first experiments. And we have already heard about the many data points on this plot here. And of course she also reproduced the ductile to brittle transition, the fast to slow. But she also showed that snow strength depends on the direction you load it. And this was really a cool result. However, we had no clue what to do with that. And needed someone like smart Sean Gom, who actually explained us then, well, we'll put that in a wider context, and he established the corresponding failure envelope. And the failure envelope simply describes how the material fails under different loading conditions, tensile on the left, shear here, and then compression on the right side. So much for failure, so much for strengths. As we all know, it's not only about failures. If we trigger avalanches, we often see these cracks. And the mechanical property that actually describes the resistance to crack propagation is fracture toughness. And this fracture toughness, no one has really looked at that for a long time. It has been in some of Dave McClung's papers, some of the equations and the adaptation of the Palmer and Rice model. Until someone from France, Helmut Kirchner, he actually sent me a letter. Sehr geehrter Herr Kollege, they had done some initial trials in the Vosges mountains, he and his colleague Gérard Michaud, and he convinced me to try some fracture toughness experiments. And of course, the first setups we had, we completely failed. We waited for hours and the snow didn't fail. We then came up with essentially two different setups, one where you have a pre-cut specimen and then you load that, or either you increase your cut length until the block fails, as we do it today in PSTs. And that was during Christian Sigrist's PhD. As you mentioned, we then went from tensile experiments also to mode 2 experiments, because of course I was convinced that this is more important than the tensile fracture. I was also convinced that interfacial fracture mechanics would work, because this bilayer approach would work. And initially we actually found that K2 decreased with increasing elastic mismatch. So if one layer is harder than the other, that would mean it would be easier for cracks to propagate. But then once we had acquired more data, the correlation was no longer significant. So we moved into the field, and here we see Siggy again with one of those first propagation experiments. And I think this was then quite successful. Siggy combined it with finite element simulations, and we could determine the first critical energy release rates of weak snowpack layers. And we kind of also established that, well, for the resistance to crack propagation, it's really the weak layer that is decisive, whereas the energy that comes to drive the crack comes from the slab. Now, we worked on fracture mechanics. We were pretty much the only ones. It wasn't really a popular subject at that time. Most studies, and in particular most field studies, were on the spatial variability and on snowpack properties and how those varied. This was a topic where you could do always a study. Many studies were done, most of them were not comparable. And the motivation for it was, on one hand side, there were some occasions when you had two stability tests side by side and you got very different results, or as you all know, maybe only the third or fourth skier would trigger the slope, which kind of suggests that there must be some hotspots out there that only wait for the skier to be touched. Now, these hotspots were also called super weak zones. So in all this spatial variability, we somehow hunted those super weak zones. A super weak zone is an area where your strength is lower than the overlying stress, or the stress from the overlying slab. And the question was, well, how is such a zone born? What is its lifespan? Will it stay there forever and wait for the skiers? And how will it disappear again? And this picture even made it on the front cover of the Winterbericht in the 1990s. It was even analyzed, and it suggested that this would kind of show spatial variability out in the field. One of the first spatial variability study you have already heard was the doctoral studies of Kalle Kronholm, one of the slopes. It's a sunny slope, you're right, and it's quite not a uniform slope, I think. And of course, we didn't find the super weak zones. There were about 20 other studies within 10 years worldwide. No one really found the super weak zone. What Kalle found was rather layer continuity than spatial heterogeneity. So the layers were usually there on all of the slope. The properties varied, but the snowpack wasn't sketchy or patchy as it was often described. So we found actually that the snowpack wasn't a Flickenteppich, but of course that picture of the Flickenteppich continued to be a very popular one among some of the practitioners. We also had some interesting experiences on one of the slopes. So here is a northwest facing slope. Here you see a grid, that famous Swiss cross, and then on the slope beside, on the northwestern face of the Hannegräte, we did another array, another grid. And so we started out in the morning on one of those days. I think you remember it were 113 S&P measurements and 24 stability tests and a profile and a Rutschblock, right? And by the way, we used the S&P in all those studies. I mean, I was quite convinced that it is a cool instrument, but it was also very, very often it broke. It was the source of major breakups. And for example, in Kalle's PhD study, we threw away half of the data. Now we, at one point in the day, one of us climbed on a pile of snow from digging and whoomph, the whole slope, which broke. We all looked up, we saw the crack opening, and luckily the slope didn't slide. We then looked at the fracture line, or at the line where the place where it actually fractured, that's right here. And then we said, okay, well, we'll just continue working. And that actually produced some really cool results. One of those several examples of reproducible research, because we then measured how that slope gained strength again, how that weak layer gained strength again within hours. Very quickly, the strength was higher than it actually has been before. So, this is one of those cool moments where you finally get a result that you don't expect, and actually that was more often the case, that we didn't find what we wanted, but we instead found something other that was also quite cool. This would have been perfect for the Journal of Irreproducible Research. Actually, it made it to GRL. So, of course, we didn't question that there is variability in the snowpack. Variability is fundamental. Disorder is fundamental. Without disorder, there wouldn't be any fractures. But some of those misconceptions, as I said, about the Flickenteppich, they just survived. The discussion, hetero versus homo, also continued for quite some time. Now, what we learned, nevertheless, or what became really important for the future spatial variability studies, is that the study design is really important. You should have actually some random sampling. You have to apply proper geostatistics. Kalle was the first one to really apply that. And then scale, scale, scale. It's really important that you think about scale at which scale you want to measure, but also if it's about spatial variability, you have to know at which scale you're talking about. Because there were those rules of thumb saying, for example, well, the more variable, the more dangerous. Well, wait a minute. If this variation is at the small scale of a meter or two, well, that slope is actually quite safe. And the next actually step that we reached with the spatial variability studies is when we put the variation, the length scale of these spatial variations in relation to critical crack lengths, to what we had learned in fracture mechanics, then it became very obvious what actually is the meaning of spatial variability for avalanche formation. And I don't know when the ideas came up, but this is one of those famous kitchen table sketches. I remember I made that in the morning at one point, just writing down what we have already seen from Joan, that the stability depends on the average stability, its variation, its standard deviation, and then the length scale of the variation. We further on made that into some nicer graphs, but on those sketches it was already laid out. So with this, I move on to avalanche formation and avalanche release. And actually quite early, we came up with this conceptual model of avalanche release from the damage process to fracture propagation. We used to call it at that time to slab release. And the most important thing is still was already there. There is failure initiation and there is crack propagation. And as you all know, this graphic kind of stood the test of time. It's still around. So we somehow got it right, but we also completely failed to put that in a model. We kind of had the feeling how it should look like, but we weren't smart enough to actually bridge this huge gap in scales between the microscale and slab release. But then at one point, this focus on failure initiation and crack propagation was really useful. You heard it before, and it also made questions about the usefulness of some of the stability tests very easy, because you could simply ask, well, does that test tell you something about initiation or propagation? We have seen the failure envelope, and this was really a crucial element, I think, for the model then Joan Gaume developed, the MPM model of slab release, which was a major step, and we all know this fancy or these nice videos, and I'm always excited to show those. I said the graphic kind of stood the test of time. This is a more modern version Stefan Harvey designed. You also see that now it's at initial failure there is natural and artificial. We looked at most of the processes then in subsequent years in more detail, and one really tricky question was, well, how do the natural avalanches form? So this is the part up here. So how does that damage process happen? How is instability developing on a slope? Can we actually follow that? Can we hear that? Can we monitor it? So we kind of hunted precursors, because if we would have a way to find those precursors, that would be great for instability. So we then worked first in the lab. Attila did that. And the little crackling noises are all the small failures, and the closer you get to your complete failure of the sample, those small cracks increase, the acoustic emission increase, and if it would be possible to measure that in a slope, that would tell us when a slope becomes unstable. And we found precursors in the lab, but if you look at the time here, it's only a few seconds before the sample actually fails, so that's not much lead time to, let's say, close a road. We then also tried to find the precursors out on the slopes. The slab bug was something that Ron Perler had coined decades before. So let's say an instrument you put into a slope and it will tell you when that slope becomes unstable. And yeah, at the time when I had acquired enough money and it was safe to do some riskier stuff in terms of not so certain research outcomes, we decided, well, we'll give it a try. There was one person who had claimed that he had found precursors. That was Hans-Uli Gubler. So we talked to Hans-Uli, we listened to him, and then we listened to the slope. And already on the first day when we deployed the sensor, we actually triggered an avalanche. And yeah, Sasha has the story on that, and you heard about this before. We were actually quite lucky as soon as we had, in the first winter, we already had an avalanche on that slope. So that is this big blue thing. That's the signal from the avalanche. But then there was something before, right here. So what we measured there was crack propagation. So we found, that was probably the first measurement of crack propagation on a slope of a real natural avalanche. Something we hadn't looked for. We completely failed to find precursors, but at least we found something useful. And what was even more useful was then when Alec analyzed that data, he found many more avalanches. Of course, he found also a lot of noise, and we'll still work on that to figure out what's an avalanche. But with this failed experiment, I think we also contributed quite a bit to paving the way towards avalanche detection. I talked about scale in the context of spatial variability. We looked a lot at the point scale and at the slope scale. I would like to move on to avalanche forecasting, and there we have to look at the regional scale. And avalanche forecasting has a long tradition, and after the disastrous event in February 1999, when also some of the forecasts weren't quite perfect, and it in general became obvious that we don't know enough about avalanche formation. At SLF, we initiated a research program on avalanche formation. And there were 5 topics, and one of them was verification. It was rather directed towards collecting validation data for the models. And it was actually quite a bit disputed why we should do that program and why we need more data. And one of the arguments was, and I quote, "Why do we try to understand avalanche formation when we can run models of it?" So I was still convinced that we need more data. I organized those verification campaigns. We had about 45 people contributing. On a single day, we would send out up to 12 teams of 2 people out into the field. We shuttled them to the mountains, 4 in 1 helicopter, and then they made their way down into the valley, doing profiles and route blocks on the way down. And here's an example of a team that just landed here and then made its way down here at the Novaya Tally near Gatschiefer. In total, we collected some 400 or 500 tests and on 8 different days, and we established the very first frequency distribution of snow stability. So this is kind of what Frank said, this data-driven approach to defining the avalanche danger levels. It was really quite cool, but I don't think we managed to convince anyone at that time what's the relevance of that for the definition of the danger levels, and it was only a couple of years since that we now have new definitions of the danger levels that are partly data-driven. Now these campaigns, they also cost me quite some sleepless nights. As you can see, sometimes the danger level was considerable. You send out 20 people, tell them to do profiles and steep slopes. And yeah, this is herding cats. I've become better at that with time. And at that time, I didn't know much about those famous human factors. But I thought, well, I sometimes have to figure out how I team up people. I cannot put two persons together who have no experience. And I prepared a questionnaire. And in the questionnaire, there was also, people had to do a self-assessment of how confident they are to assess the avalanche danger. And there were a decent number of young males who actually thought they can really do it. And what I learned is, okay, it's probably not a good idea to put two of them together in one team. Better pair them with someone else who is maybe less certain of his skills. And it was quite common that, for example, the avalanche forecasters checked the second highest box here. So much for my human factor knowledge and experience. Interestingly, at about the same time, I was asked by the Scottish Avalanche Foundation to give a talk on heuristic traps in avalanche decision making. And I told them, well, listen, I have no clue about this. This is really the topic of Ian McCammon. And they said, yeah. And well, it had happened that I had published a paper with Ian in the same year when he talked at the ISSW about the heuristic trap. So maybe they mixed something up. But then, yeah, of course, they also asked me about talks on stability, and I finally agreed. But then I thought, well, I'm not just going to take Ian's presentation and present it in Scotland. So I thought, well, maybe I'll look a little bit at how in my career these heuristic traps could have played a role, and what kind of mistakes I made in decision making. So I made a little statistics on all the unexpected avalanches I had triggered, or some were also naturals. That was the statistic at that time. It was a quite exceptional year in '94. I later on updated, and yeah, you can ask then yourself, well, if you're a lot in the mountains, a lot skiing, doing field work, well, it's quite normal that you trigger avalanches, and it's an uncertain business, so what should we care about? Or yeah, maybe there are some real decision-making errors. I updated that graph some time later, and yeah, it didn't really improve. Also, I probably had to read some papers in between about human factors. And then Ian had suggested what he called the hazard score. So that's how many signs of instability you actually have on a particular day. And of course, the higher that number is, the less it makes sense to trigger an avalanche and venture out in the backcountry. And there are some number 4s, not number 7s, but some higher numbers. So yeah, I was probably overconfident at sometimes in my career. And if you look at what happened, if I look at some of the events, so in the early 90s, I joined SLF. We were up on the Weisfurjoch. I was probably quite confident in assessing the avalanche danger. Probably I would have also ticked the box. Very good. Then there's a little dip here. Don't know, 3 kids were born in between. Then it continued. So following Bruce Tramper's book, you can sketch something, the blue line, like your confidence in avalanche skills, and usually it goes up, and then an avalanche happens, it goes down, and so on and so forth, and I don't know, somewhere around here, probably right now. So that was an interesting experience, and I recommend to everyone to actually do that and keep track of all the stupid things you do along the line. Yeah. Now, to conclude on avalanche formation, when we did that first review paper, we had some open questions. One of those nice blue graphs. And many of those I think we worked on. We also made quite some progress. We heard that texture and mechanical properties is still a hot topic. We don't really have, or we're not able to relate mechanical properties to the microstructure. But a lot of the other things worked. So part 3, application. When I started ASLF, I worked on fairly application-oriented projects. Actually, 2 of them. One was gear triggering, and the other was numerical forecasting. And in gear triggering, I think we made good progress, and what we found out there actually made it quite quickly into practice and also into the bulletin. So we see Christian Campanovo here. So we established that, of course, that was known from theory that our impact as skiers decreases with steps. It also depends on the layering. And today, it's quite common that you have a sentence like Vorsicht vor allem an eher schneearmen Stellen sowie an Übergängen von wenig zu viel Schnee. So that's exactly, these are the findings that we had in the studies. They still talk about Entlastungsabstände, although we showed that those are not relevant because if you walk behind, the impact actually doesn't add up. Now, numerical forecasting was less successful. On one hand side, if you look at the performance measures of those simple models we had at that time, of those expert systems, those are pretty much the same as today. We also use pretty much the same methods, neural networks, for example. And yeah, the models were quite cool, but maybe we were ahead of time, and we were certainly completely incompetent in turning those models into operational models. I mean, those were toy models. You had to enter data manually. You couldn't scale it up to the area, let's say, of the Swiss Alps. So it took another 20 years. And there was a big hype about artificial intelligence, actually, at that time. Kind of goes in circles. Yeah, we have heard, I think it was always important to me to also be involved in education, to pass on the knowledge. One of the first things we did was this leaflet, Achtung Lawinen, that since then appeared in the 8th edition. And I think here we really had, in social sciences, you would call this today transformative relations with stakeholders, because in every single edition we actually added some research and changed some of the things and how we assess avalanche danger. And the courses have been mentioned before. I think this is also a good way how we were able to transfer the knowledge. Another topic I had to work on were accident investigations. And this is pretty a humble experience. It's a brutal reality check. And it shows you that you don't know very much. And it was always a great learning experience, and it was also a motivation to actually continue and to dig deeper and to really try to understand avalanche formation. And also, if you get on those scenes and if you look at the terrain, if you look at the snowpack, in probably half of the cases, I also had to say, well, this could have also happened to me. Independent tests were a chapter we were also quite involved at some times. So we tested transceivers, we tested avalanche airbags. That was not an easy task. We got lots of angry letters from manufacturers, registered mail, registered letters. But I think it was, in terms of the service we provided to the consumers, to the users, it was quite useful. The last independent test we did was in artificial avalanche control, on these remote systems of avalanche control. We sent in our jetty masts and, of course, left the Gazek. So there are two different methods, essentially with solid explosive or exploding gas mixture. And it was very difficult to get everyone on the table here, in particular the Kazakhs people. They didn't really trust us. Took us almost 2 years and some speed sightseeing in Milano, as you have heard, to actually do these tests. And that's the setup we came up with. So here's the Kazakhs, and then on some of the poles right here, we would have the solid explosive measuring from this side and the Kazakhs from that side. And how I convinced, we did that on the firing range in Hinterrhein, and how I convinced the military to allow us to do that, that would be another story. Okay, so this is the Big Bang. And here we also, let's say, completely failed to convey the message. I mean, it was quite clear that the impact of the two different methods is quite similar, but that wasn't what people wanted to hear. So, there we go. One last result of that wonderful aero-producible research, some of those exciting moments. We have already seen the video, I think. We did dig hole, we watched the snowpack, what was happening with video cameras. The explosion will be here, somewhere out on the right. And you will see the pressure waves coming in, if you focus on this area here, and then you will also see how the snowpack settles, because behind the pressure wave travels the crack in the weak layer fails and the snowpack settles. Look here, and now the snowpack settles. Hard to see, but irreproducible research. Some of the most exciting side projects I could afford in the last 10 years were together with the group of medical doctors in Bozen. They took out the whole of almost all the instruments of an emergency room, went out into the field. At one point we tried to find out what's the influence of snow density on how you can breathe if you are below the snow. We scheduled experiments in January, February, and March, hoping then we would have cold snow in January, some warmer snow, and so on. Well, didn't work at all. We hardly got a relation with density, but it was always very cool and very exciting field work. And yes, yeah, you have seen a lot of pictures now of mostly sunny weather. You've seen a lot of field work. And I think this is really an important component. First of all, I've learned a lot in the field. It's also great to work in the field with teams. In some of those projects, we were 4 or 6, and it's, I think, one of the most rewarding things if you get the full day of field work done, get down to the valley, and it's usually a nice evening. And why do we go into the field? I think even today, with machine learning or artificial intelligence, however good the model is going to be, well, if we don't have sufficient process understanding and actually stick our nose into the snow from time to time, we will not understand and will not be able to value and validate these results. So avalanches are really best studied in their native habitat. And fieldwork is also cool. I mean, I don't have many pictures of from the office with a lot of good laughs, but in the field that is way more common, and we had often really good times, hard times in between, as we also have heard today. Not always nice weather like here, but it was a wonderful time to work with all these people and with all the students. Here are a few. Some were on stage already today. There are many more. It's once again only a little selection. And I would like to thank them all. Thank also you for showing up today and for this incredible experience today. My apologies for when I sometimes looked in a different directions, or sometimes I was a little bit rude. It wasn't intended. I wasn't intended to hurt anyone. I also particularly like everyone who made that journey possible, in particular Connie and the kids. And yeah, don't forget to have fun.
Yes.